Presentation of the wattmeter system for measuring magnetic losses as a function of temperature. The sample consists of a cobalt-iron vacuum or cobalt-iron vacuum-flux toroids or cobalt-iron or iron silicon strips to be measured with the Epstein frame method. To measure the toroidal sample, two windings must be made, one primary to induce the magnetic field and another secondary to acquire the induced voltage data. The Epstein frame is a device with standardized shape and dimensions, standard 6040402, for measuring the property of soft magnetic lamination strips. Each side of the square is provided with a secondary and, external to it, a primary winding and wrapped on a rigid insulating former having rectangular cross-section. The solenoids have all the same number of turns and each of them cover the same length of 19 cm. There is a total of 700 primary magnetizing and 700 secondary turns in the frame used for DC and power frequency measurements. The four solenoids are series connected, somewhat emulating uniformly distributed winding. The specimen is composed of 4 or a multiple of 4 strips of width 30 mm and length variable from 280 to 320 mm for a minimum mass of 200 grams. The flux continuity at the square corners is ensured by double-lapped joints. A weight of 1 Newton placed on each corner joint provides good and reproducible flux closure. This is the Epstein frame recommended for medium frequency testing from 400 Hz until 10 kHz, standard ESC 6040410, with a total of 200 turns. We present the specific case of the measurement on the cobalt-iron vacuum toroidal sample. We insert the sample into the thermal cell and set the temperature. We leave the necessary time for the specimen temperature to stabilize. The Wattmeter hysteresis graph developed at EMPIR for the characterization of soft magnetic materials is composed by the following main elements: arbitrary function generator, circuit breaker, signal symmetrizer, power amplifier, interface board made up of the load and measurement resistors, for low frequency from 1 to 20 Hz to SRS low noise signal amplifiers, acquirer for channel oscilloscope. The program developed with an Agilent VEE Pro 7.0 software, which is the brain of the system. The calculation program requires some input data, among which one of the most important is the cross-sectional area of the sample. This is calculated from the mass weight with the certified balance, the density of the material, and the dimensions measured with the certified caliper. Other input data are number of turns of primary and secondary winding, the mass density of the material, magnetic path length, total resistance of the primary circuit and the reference resistance in the primary circuit, the cross-sectional area, the amplification factor of the power amplifier, and turn area of the secondary winding, which is 0 with compensated Epstein frame. We set the desired frequency F and the peak induction BP, in fact the polarization JP equal BP minus mu0H, and with repeated attempts, we give a voltage necessary to obtain the preset polarization. We adjust the oscilloscope setting to obtain a waveform of at least 1.5 period, the amplitude so that it is completely visible on the screen, and the sine wave shape. Very frequent, the result is not achieved on the first attempt, so a series of feedback routine is carried out to refine the results. Once the desired polarization at the form factor 1.1107 plus minus 0.1% have been obtained, we acquire the measurement and record the value of the losses, which represent the area of the hysteresis loop. Normally, the temperature affects the value of the losses, causing the losses decrease as the temperature increase. In the specific case of cobalt iron, we have observed a different behavior. The loss has a minimum value at room temperature. The more you move away from the ambient temperature in a positive or negative sense, the more the losses increases. The phenomenon is partly due to the anisotropy and partly to the magnetostriction of the material. The cobalt iron alloy has a high magnetostriction coefficient.